Today we are going to learn monotonic sequences. Monotonic sequences. Monotone sequences. Definition of monotonic sequences. Definition. Let sequences n is equal to 1 to infinity be the sequence of real numbers. If S1 less than or equal to S2, less than or equal to S3, less than or equal to and so on, S suffix capital N less than or equal to S suffix capital N plus 1, less than or equal to and so on, Sn less than or equal to Sn plus 1, less than or equal to and so on. Then we say that sequence Sn n is equal to 1 to infinity is non-decreasing sequence. If S1 less than or equal to S2 less than or equal to S3 less than or equal to S suffix capital N less than or equal to S suffix capital N plus 1 less than or equal to and so on S suffix small n less than or equal to S suffix small n plus 1 less than or equal to and so on. Here small n is greater than capital N. Since 1 is less than 2, 2 is less than 3, 3 is less than 4, capital N is less than capital N plus 1 and so on, capital N is also less than small n. That is small n is greater than capital N. If S1 greater than or equal to S2, greater than or equal to S3, greater than or equal to and so on, greater than or equal to S suffix capital N, greater than or equal to S suffix capital N plus 1, greater than or equal to and so on, greater than or equal to Sn, greater than or equal to Sn plus 1 and so on. Then we say that sequence Sn n is equal to 1 to infinity is non-increasing sequence. A sequence S is equal to Sn. A sequence Sn n is equal to 1 to infinity of real numbers is said to be monotonic sequence if it is either non-decreasing or non-increasing or both. A sequence Sn n is equal to 1 to infinity is called as monotonic sequence. Monotonic sequence if the sequence Sn n is equal to 1 to infinity is either non-decreasing or non-increasing sequence or both. For example, Consider the sequence Sn n is equal to 1 to infinity. Consider the sequence S suffix n is equal to 1 to infinity, where number 1, Sn is equal to n square for all n belongs to I. This sequence is 1 square, 2 square, 3 square, 4 square and so on. 1 square is 1, 2 square is 4, 3 square is 9, 4 square is 16 and so on. First term is S1 less than or equal to S2, S2 less than or equal to S3, S3 less than or equal to S4 and so on. Therefore, the sequence Sn n is equal to 1 to infinity is non-decreasing but not non-increasing. The sequence Sn n is equal to 1 to infinity is non-decreasing but not non-increasing. The sequence is non-decreasing sequence of real numbers. It is not non-increasing sequence of real number. Second example, Sn is equal to 1 by n for all n belongs to I. This is equal to, first term is 1, 1 by 2, 1 by 3, 1 by 4 and so on. S1 is greater than S2, S2 is greater than S3, S3 is greater than S4 and so on. Therefore, the sequence Sn, this is sequence Sn, the sequence S suffix n is equal to 1 to infinity is non-increasing sequence, non-increasing but not non-decreasing sequence, but not non-decreasing sequence. Number 3, third example, Sn is equal to k for all n belongs to I, where k is constant. Where k is constant for all n belongs to I. That sequence is, first term is k, second term is k, third term is k and so on. This sequence is non-decreasing and it is also non-increasing. Therefore, Sn n is equal to 1 to infinity is both the sequence S suffix n is equal to 1 to infinity is both non-decreasing and non-increasing sequence. Non-decreasing and non-increasing sequence equal to S1 equals S2, S2 equals S3, S3 equals S4 and so on. Number 4, Sn is equal to minus 1 to the power n for all n belongs to I. This sequence is minus 1 plus 1, minus 1 plus 1, minus 1 plus 1 and so on. S1 is minus 1, S1 is less than S2. but S2 is not less than S3. This sequence is neither non-decreasing nor non-increasing. This sequence Sn, n is equal to 1 to infinity, is equal to minus 1 to the power n is equal to 1 to infinity, is neither non-decreasing nor non-increasing sequence of real numbers. The examples above, that is sequence first, Sn is equal to n square, Sn is equal to 1 upon n, Sn is equal to k. The sequences in 1, 2 and 3 are monotonic sequences. The sequences in first, second, third are monotonic sequences. The sequence in 4 is not monotonic sequence. Monotonic sequence. Now we see the theorem number 1. A non-decreasing sequence which is bounded above is convergent. A non-decreasing sequence which is bounded above is convergent. Proof of this theorem. Let sequence Sn n is equal to 1 to infinity be the sequence of real numbers. Sequence Sn n is equal to 1 to infinity is sequence of real numbers. Suppose sequence Sn n is equal to 1 to infinity is non-decreasing and bounded above sequence. Therefore, by definition of bounded sequence, by definition of bounded sequence, the range set capital A is equal to S1, S2, S3 and so on is non-empty subset of R. Non-empty subset of R set of real number R, set of real number R. The range set capital A is non-empty subset of R and is bounded above Capital A is the range set of the sequence Sn. Since S is equal to Sn, n is equal to 1 to infinity is the function from the set I of all positive integers into the set R of all real numbers. Therefore, the range set A is equal to S1, S2, S3. These are the elements of a range set. And capital A is non-empty subset of R and it is bounded above. Let capital M is equal to list upper bound LUB of the set S1, S2, S3 and so on. It is bounded above, therefore it has upper bound. Therefore capital M is list upper bound of the set A, LUB for set A, capital A. We claim limit n tends to infinity of Sn is equal to M. We have to show that. We claim limit n tends to infinity of Sn is equal to capital M. Limit n tends to infinity of Sn is equal to capital M. Since capital M is list upper bound for set A, therefore, since capital M is list upper bound LUB for set capital A, therefore, we write S suffix n is less than or equal to capital M for all n belongs to I. This statement says that S1 is bounded above by M, S2 is bounded above by capital M, S3 is bounded above by capital M, Sn plus 1 is also bounded above by M and so on. Sn is bounded above by capital M. For any epsilon positive, capital M is strictly less than capital M plus epsilon is trivially true. Since epsilon is positive, therefore M plus epsilon is greater than capital M. Therefore, from 1 and 2, we write Sn less than or equal to capital M, and capital M is less than capital M plus epsilon. Capital M plus epsilon. And this is true for all n belongs to I. Every n belongs to I. For every positive integer n. Therefore, Sn is less than capital M plus epsilon for all n belongs to I. This is relation number 3. For any given epsilon positive, since capital M is LUB for the set A, capital A. Since capital M is LUB, list upper bound, for the set capital E, or the set capital E. For any given epsilon positive, greater than 0, M minus epsilon, capital M minus epsilon is not an upper bond, is not an upper bond for the set capital A, for the set capital A. M minus epsilon is not an upper bond for the set capital A, capital A. Therefore, there exists positive integer n, capital N, a term of the sequence Sn is equal to 1 to infinity such that m minus epsilon is less than s suffix capital N. Hence, there is capital N belongs to I, capital N belongs to I, such that capital M minus epsilon is less than s suffix capital N. Hence, there exists positive integer n belongs to I, such that s suffix capital N is greater than m minus epsilon, or m minus epsilon is less than s suffix capital N. This is step 4, relation 4. Since by hypothesis sequence s suffix n is equal to 1 to infinity is non-decreasing sequence. Therefore, by definition of non-decreasing sequence, by definition of non-decreasing sequence, S1 less than or equal to S2, S2 less than or equal to S3, and S3 less than or equal to, and so on, S suffix capital N less than or equal to S suffix capital N plus 1 less than or equal to, and so on, less than or equal to S suffix small n less than or equal to S suffix small n plus 1 less than or equal to, and so on. That is, S suffix capital N is less than S suffix small n for all small n is greater than capital N. Since 3 is greater than 1, S1 is less than S3. Therefore, in short, we write S suffix capital N is less than or equal to S suffix small n for all small n is greater than or equal to capital N. Value of this small n is greater than capital N since 3 is greater than 1. 3 is greater than 2. Therefore, n is greater than capital N. Small n is greater than capital N. This is step 5, relation number 5. From 4 and 5. From 4 and 5. 4 and 5, we write m minus epsilon, capital M minus epsilon, less than Sn, less than or equal to S suffix small n. This is true for all n greater than or equal to capital N. That is, capital M minus epsilon less than Sn for all n greater than or equal to capital N. This is a 6. Relation 6 is true for all small n is equal to capital N plus 1, capital N plus 2, and so on. Relation 6 is true for all small n is equal to capital N plus 1 and so on. Relation 3 is true for all n belongs to I. It means relation 3 is true for n is equal to 1, n is equal to 2, n is equal to 3 and so on. This small n is equal to capital N. Small n is equal to capital N plus 1 and so on. Therefore, from 6 and 3 we write, from 6 and 3 we write m minus epsilon, capital M minus epsilon less than Sn. And this Sn is less than capital M plus epsilon. And this is true for all small n greater than or equal to capital N. This is true for all small n greater than or equal to capital M. Subtracting minus m, we obtain minus epsilon less than Sn minus m, less than epsilon for all small n greater than or equal to capital N. By properties of modulus, we write modulus of Sn minus capital M is less than epsilon for all n greater than or equal to capital N. By definition of limit of sequence, by definition of limit of sequence, sequence Sn, limit n tends to infinity of Sn is equal to capital M. N tends to infinity of Sn is equal to capital M. That is, capital M is limit of sequence Sn. By definition of convergent sequence. By definition of convergent sequence. Sequence S suffix n is equal to 1 to infinity is convergent to capital M, hence the proof of the theorem. Now we see corollary. The sequence 1 plus 1 upon n bracket raised to n is equal to 1 to infinity is convergent. The sequence 1 plus 1 by n raised to n is equal to 1 to infinity is convergent. Proof of this corollary, let Sn is equal to 1 plus 1 upon n raised to n for all n belongs to I. Given sequence is Sn is equal to 1 plus 1 upon n raised to n for all n belongs to I. By binomial expansion, we expand RHS. That is, Sn is by binomial expansion. Binomial expansion or binomial theorem. Sn is equal to 1 plus 1 upon n raised to n is equal to first term is 1 raised to n is 1 plus n into 1 by n second term plus third term n into n minus 1 upon 1 into 2 2 into 1 by n square plus n into n minus 1 into n minus 2 upon 1 into 2 into 3 into 1 upon n raised to 3 plus and so on, plus and so on. NC0 1, NC1 n, NC2 is n into n minus 1 upon 2 factorial. NC3 n into n minus 1, n minus 2 upon 1 into 2 into 3 into 1 upon n raised to 3. Now we write k plus first term. K plus first term. This is first term. This is second term. This is third term. This is fourth term of the expansion. Now we write k plus 1th term. K plus 1th term plus n into n minus 1, n minus 2 and so on n minus k minus 1 upon 1 into 2 into 3 and so on k into 1 upon n raised to k plus and so on, and last term is plus n into n minus 1, n minus 2 and so on. Last term is 3 into 2 into 1 upon 1 into 2 into 3 into and so on n into 1 upon n raised to n. By using binomial expansion, 1 plus 1 upon n raised to n is equal to this value. Now, this is first term, this is second term, this is third term, this is fourth term, and this is k plus first term of the sequence. For k is equal to 1, 2, 3 and so on up to n. For k is equal to 1, 2, 3, 4 and so on up to n, the k plus first term of Sn is of sequence Sn is of sequence S suffix n is equal to this term n into n minus 1, n minus 2 and so on. Last term is n minus k minus 1 bracket complete upon 1 into 2 into 3 and so on up to k into 1 by n raised to k is equal to 1 over 1 into 2 into 3 and so on up to k. N raised to k is n into n and so on n k times, since n into n, n square, n into n into n, n cube, n into n into n into n, n raised to 4. Therefore, n raised to k can be written as n into n into n and so on n k times. N numerator contains k terms, n into n minus 1 into n minus 2 and so on n minus k minus 1 upon n raised to k can be written as n into n and so on up to n. We divide numerator by this n and we write 1 upon 1 into 2 into 3 and so on up to k into n by n is 1, n minus 1 by n minus 2 by n and so on, n minus k minus 1 upon n is equal to 1 upon 1 into 2 into 3 and so on up to k. N cancels. N by n becomes 1 minus 1 by n. N minus 2 by n becomes 1 minus 2 by n. Next term is 1 minus 3 by n and so on. Last bracket is 1 minus k minus 1 by n. 1 minus k by n. This is equation 1. This is relation 2. This is k plus first term of the sequence Sn. Now, if we expand Sn plus 1, we obtain n plus 2 terms, one more than for Sn. Now, if we expand Sn plus 1, we obtain n plus 2 terms, n plus 2 terms. One more than for Sn. One more than for Sn. That is, Sn plus 1 contains n plus 2 terms and Sn contains n plus 1 terms. N plus 1 terms. Therefore, the k plus for, we write here, for k is equal to 1, 2, 3 and so on n. The k plus first term of sequence Sn plus 1 is k plus first term of the sequence Sn plus 1 is equal to, we write 1 upon 1 into 2 into 3 and so on up to k. This is k plus first term of Sn. Replace n by n plus 1, we obtain k plus first term of the sequence Sn plus 1, and it is equal to 1 minus 1 upon n plus 1 into 1 minus 2 upon n plus 1 into 1 minus 3 upon n plus 1 and so on. Last term is 1 minus k minus 1 upon n plus 1, k plus 1. This is say 3. The quantity in 3 is greater than quantity in 1, quantity in 2, which is greater than quantity in 2. How it is greater than? Since n is less than n plus 1. This is true for all n belongs to I. Therefore, 1 upon n is greater than 1 upon n plus 1. Multiplying by minus 1 upon n is greater than minus 1 upon n plus 1. Adding 1, we obtain 1 minus 1 by n is greater than 1 minus 1 upon n plus 1. Multiplying by minus 1, there is small mistake. Multiplying by minus 1, we obtain minus 1 upon n is greater than minus 1 upon n plus 1. 1 minus 1 upon n plus 1 is greater than n is less than n plus 1. 1 upon n is greater than 1 upon n plus 1. Multiplying by minus 1, we obtain multiplying by minus 1 minus 1 upon n is less than minus 1 upon n plus 1. Therefore, 1 minus 1 upon n is less than 1 minus 1 upon n plus 1. 1 minus 1 upon n is less than 1 minus 1 upon n plus 1. Means first bracket 1 minus 1 upon n is less than 1 minus 1 upon n plus 1. Again, here n is less than n plus 1 is true for all n belongs to I. All n belongs to I. Therefore, 1 upon n is greater than 1 upon n plus 1. Multiplying by minus minus 2 upon n is less than minus 2 upon n plus 1. Minus 2 upon n plus 1. Adding 1 minus 2 by n is less than 1 minus 2 by n plus 1. N plus 1. And so on. And so on. This means that this term, this second bracket, 1 minus 2 by n is less than 1 minus 2 by n plus 1. And so on, we write 1 minus k minus 1 by n is also less than 1 minus k minus 1 upon n plus 1. This is true for every n belongs to I. Therefore, each bracket in 2 is less than or equal to, strictly less than the corresponding bracket in 3. Every bracket in 2 is less than or equal to corresponding bracket in 3. Therefore, the quantity in 3 is greater than, therefore, the quantity 3 is greater than the quantity in 2. The quantity in 2. This means the term k plus first term of Sn plus 1 is greater than k plus first term of Sn. Also, Sn plus 1 contains one more term. Therefore, Sn is less than or equal to Sn plus 1 for all n belongs to I. That is S1 less than or equal to S2 for n is equal to 1. For n is equal to 2, S2 is less than or equal to S3, less than or equal to, and so on, less than or equal to Sn less than or equal to Sn plus 1, less than or equal to, and so on. Therefore, this sequence Sn, n is equal to 1 to infinity, is non-decreasing sequence of real number. Non-decreasing sequence of real numbers. Non-decreasing sequence of real numbers. This is a relation 1, 2, 3, 4. This statement is a 4. Sn is non-decreasing. Sn is non-decreasing. Now we show, we have to claim or we have to prove this non-decreasing sequence is bounded above. Therefore, by theorem 1, a non-decreasing sequence which is bounded above is convergent. Therefore, Sn n is equal to 1 to infinity is convergent. From 2, Sn is equal to 1 plus n into 1 by n plus n into n minus 1 upon 1 into 2 plus n into n minus 1 into n minus 2 upon 1, 2 into 3 into 1 upon n raised to 3. Here is 1 upon n square. Plus and so on. Last term n into n minus 1, n minus 2 and so on. 2 into 1 upon 1 into 2 into 3 and so on up to n into 1 by n raised to n. From relation 1, Sn is equal to 1 plus n into 1 by n plus n into n minus 1 upon 1 into 2 into 1 by n square plus n into n minus 1 n minus 2 upon 1 into 2 into 3 plus 1 upon n raised to 3 plus and so on n into n minus 1 n minus 2 and so on 2 into 1 upon 1 into 2 into 3 and so on up to n into 1 upon n raised to n. This is equal to 1 plus 1 plus 1 upon 1 into 2 into n by n into n minus 1 by n plus 1 upon 1 into 2 into 3 into n by n into n minus 1 by n into n minus 2 by n. N cube is equal to n into n into n. Plus and so on. Last term is 1 upon 1 into 2 into 3 and so on up to n into n by n into n minus 1 by n into n minus 2 by n and so on. Last term is n minus 1 upon n. N raised to n is n into n into n times. This is equal to 1 plus 1 plus 1 upon 1 into 2 plus 1 into n cancels. N by n is 1. N by n is 1. Therefore, 1 minus 1 by n. Next term, 1 upon 1 into 2 into 3 into n cancels. 1 minus 1 by n into 1 minus 2 by n plus and so on. Last term is plus 1 over 1 into 2 into 3 and so on up to n. N cancels and n minus 1 upon n becomes 1 minus 1 by n into 1 minus 2 by n and so on. 1 minus n minus 1 upon n. Simplification above becomes 1 plus 1 plus and so on. Now each bracket is 1 minus 1 upon n, 1 minus 2 upon n, next is 1 minus 3 upon n and so on. Therefore we replace this bracket is less than 1, less than 1, and this is less than or equal to 1 plus 1 plus 1 by 2 into 1 plus 1 upon 2 into 3 into 1 into 1 plus and so on plus 1 upon 1 into 2 into 3 and so on up to n, and each bracket is less than 1, that is less than 1 and so on, it is less than or equal to 1. Therefore, Sn is less than or equal to, Sn is less than or equal to 1 plus 1 upon 2 plus 1 upon 2 into 3, 1 upon 2 into 1 upon 3. Next term is 1 upon 2 into 1 upon 3 into 1 upon 4. Plus and so on. Last term is, and so on, last term is 1 upon 2 into 1 upon 3 into and so on 1 upon n. Clearly, trivially, 2 is less than 3, or 3 is greater than 2. Therefore, 1 upon 3 is less than 1 by 2. 1 by 2. Again, 4 is greater than 2. Therefore, we write 1 by 4 is less than 1 by 2. Again, there is 1 by 5. Next term contains 1 by 5. 5 is greater than 2. 5 is greater than 2. Therefore, 1 upon 5 is less than 1 by 2. We replace 1 by 3, 1 by 4, 1 by 5 and so on by 1 by 2. And we write Sn is less than or equal to 1 plus 1 by 2 plus 1 by 2 into 1 by 2 plus 1 by 2 into 1 by 2 into 1 by 2. 2 into 2 into 2 if it is 4 factorial, 1 into 3 into 4. This is n plus and so on plus 1 upon 2 to the power n minus 1. There are 3 terms, that is actually 4 factorial, 1 into 2 into 3 into 4, 4 factorial. 4 factorial, 2 raised to 3, 4 minus 1. Here is n factorial, therefore 2 to the power n minus 1. Therefore, Sn is less than or equal to 1 plus 1 by 2 plus 1 upon 2 square plus 1 upon 2 raised to 3 plus and so on plus 1 upon 2 to the power n minus 1, n minus 1. From second term, 1 plus half plus 1 upon 2 square plus 1 upon 3 square plus and so on, addition of these numbers. If we divide third term by second term, we obtain 1 half. If we divide next term 1 by 2 square by 1 half, we obtain 1 half. Again we divide 1 upon 2 raised to 3 by 1 upon 2 raised to 2, we obtain 1 by 2. Therefore, this is geometric series whose common ratio R is equal to 1 by 2 and first term is 1. Therefore, addition of these terms equal to Sn less than or equal to 1 plus first term 1 into bracket 1 minus common ratio 1 by 2 raised to how many terms? 2 to the power n minus 1 is last term, and here is 2 raised to 0. 2 raised to 0 is 1. that is 1 by 1. Means these are n terms, 1 upon 2 to the power n upon 1 minus common ratio, that is 1 minus half. And this is equal to 1 plus 1 minus 1 upon 2 raised to n upon 1 minus half, 1 minus half. Again, numerator is 1 minus 2 raised to n. As n tends to infinity, this term becomes 0. That is 1 minus, therefore less than 1. We replace it by less than 1. Therefore, Sn is less than 1 plus 1 upon 1 minus half. 1 minus half is again half, is equal to 1 plus 1 upon 1 by 2 is equal to 1 plus 2 is equal to 3. Therefore, Sn is less than 3. Sn is less than 3 for all n belongs to I, or every n belongs to I. Since result 1 is true for all n belongs to I. Therefore, all steps are true for all n belongs to I. All n belongs to I. Therefore, sequence Sn n is equal to 1 to infinity is bounded above by 3. Bounded above by 3. This is a fifth equation. Sn is bounded above by 3. Sn is non-decreasing in 4. We know theorem 1. We know theorem 1. Theorem 1. A non-decreasing sequence which is bounded above is convergent. This is a 6. Therefore, from 4, 5 and 6, from 4, 5 and 6. For Sn is non-decreasing sequence of real number. Sn is non-decreasing sequence of real number. 5 is non-decreasing sequence. Sn is bounded above. 6 is theorem. A non-decreasing sequence which is bounded above is convergent. Therefore, sequence Sn n is equal to 1 to infinity is convergent. Sequence Sn n is equal to 1 to infinity is convergent. Sequence Sn means 1 plus 1 upon n raised to n is equal to 1 to infinity is convergent. Hence the proof of corollary. Of corollary. Note, we write, note, limit n tends to infinity of 1 plus 1 upon n is equal to E. Note, limit, we note that limit n tends to infinity of Sn is equal to limit n tends to infinity of 1 plus 1 by n raised to n is equal to E, where 2 is less than E is less than 3. Actual value is 2.7184 and so on.